experiment design. Okay, so let me summarize classic experiment design, which apparently I didn't record, okay? When you're looking around your world, the explorer has to start with the gift of a question. They have to be open to curiosity. They look around the world, they say, wow, that's interesting. Why or what or how? And it could be biological, chemical, or physical. And so you want to understand how something is working. And so a simple example is a germinating seed. You want to understand germination in that seed, but you recognize you can't just study the seed. It has to be in some kind of environment. You need to have a soil, a growth medium with a certain composition, atmosphere with a certain composition, maybe light if you want to see after germination, a temperature. And so as soon as you understand that you're studying something in an environment, you have to add the word system to it. You're studying a biological system, a chemical system, or a physical system. And we can rename that set of characteristics as variables. The reason being that you can vary them. And the reason you would want to vary them is you want to understand the role of the variables on what you're studying. But you can't vary all of them at once, because if you do that, you don't know which variable is responsible for the behavioral change you're seeing. So in classic experiment design, you want to keep all the variables constant. Change one, we call it the independent variable. And we pick the independent variable of all of the possible variables in that environment based on the original essential question that's driving the journey, the problem to be solved. And often you will need to do an experiment not just on the unknown quantity, say these specific seeds, but you need to compare that to something known, and we call that the control experiment. I know that that was a really fast overview of classic experiment design, but shame on me for not hitting the record button. So, okay, so now let's get to microgravity experiment design. So I asked before, does anybody know a variable that plays a critical role in virtually anything I want to study, but it's often taken for granted? And somebody called out gravity. And yes, gravity plays a critical role in virtually anything we want to study. And so let's say that all of the questions associated with SSEP are one particular flavor of question. What is the role of gravity in this or that other thing? So if that's the case, as you said before, I need to change the gravity variable to see what happens, but I can't. And I'll explain that in a moment. Let me give you some examples of the role of gravity in the world around us. And virtually everything, gravity plays a role in virtually everything you want to study because it's being studied in gravity. And so even a germinating seed knows about gravity because when it germinates, the roots go down, the shoots go up. It's called geotropism. Your body knows about gravity in myriad ways. As an example, every time you take a step under your own weight, it causes a compression of your bones, which sends a bioelectrical feedback to your body saying, bones are good, keep making those bones. But when you go to an environment where gravity seems to disappear, like aboard the International Space Station, the astronauts appear to be weightless, which means that there is no bone compression, and the body says, we don't need bones. And the body starts excreting the skeletal system. And that's why astronauts have to use straps and pulleys to force compression of the bones to minimize bone decalcification. And if anybody is a fan of the movie WALL-E, well, you know what I'm talking about here. So gravity plays a critical role in virtually anything we want to study. But okay, we can't change gravity because of this. The force of gravity is exerted by all of the mass of planet Earth on you. The mountain ranges, the oceans, the crust, the mantle, the core, all of the mass of this big sphere we're living on is pulling down on you with a force of gravity. Does anybody know what we call the force of gravity exerted by Earth on you?
Weight.
Your weight. And gravity must be a pretty weak force, because if you get on your bathroom scale and you see you weigh 150 pounds, it took the entire mass of Earth pulling down on you to give rise to that force pulling down of 150 pounds. And by the way, the force of gravity exerted by Earth on you is not just coming from the stuff under your feet. It's coming from the mass on the other side of the planet, which is also pulling down on you from a distance of 12,000 kilometers away. So if I want to change the force of gravity, I have a problem. I'm living on this. What do you think happens to the force of gravity if you move farther from Earth?
It's smaller.
It diminishes, right? It goes down.
Yep.
So maybe if I take my experiment into space, I'm going far enough away from the Earth for gravity to be changed. So if I run my experiment there, it will be running at a lower gravity. Does that make sense? What is the diameter of the Earth?
About about 6,400 kilometers.
Actually, that's the radius. So
Yeah,
it's about
bigger.
12,000 kilometers diameter, 8,000 miles diameter. Let's work in miles because it's a bridge to the familiar. How far does the International Space Station orbit the Earth? How far above the Earth does the International Space Station orbit?
300 miles.
It's about 200, close. It's about 250 miles. So remember those two numbers. So the tallest mountain on Earth is?
Mount Everest.
Mount Everest. Let's say I could find a mountain 47 times higher than Mount Everest. 47 times higher than Mount Everest. That would be a way cool mountain. And the reason it's way cool is when I go to the top of that mountain, I will be 250 miles above the surface of the Earth, the same distance above the Earth as the International Space Station. And I could stand on that mountain 47 times higher than Mount Everest and watch the International Space Station fly by my face. And I look inside the big window, and the astronauts, what are they doing?
Right.
What are the astronauts doing when I look in that big window on the International Space Station?
They're floating.
They're floating around as if gravity does not exist, right? They're floating around as if gravity doesn't exist. But here's the problem. I'm at the same height above the Earth as the International Space Station astronauts. I bring my trusty bathroom scale wherever I go. I'm talking to a therapist about that. Don't worry about that. I bring my trusty bathroom scale wherever I go, and I put it down on this mountain, and I see the astronauts floating around as they fly by me, and I look down on my scale, and I weigh almost the same as what I weigh on the surface of the Earth, 90%. Why is that?
Because I mean, you are standing over there, you are not moving, and the astronauts, they are, I mean, in the place circling around the Earth.
Okay, so yes, so we're going to get to that in a minute. Why am I 90% of what I weigh on the surface of the Earth?
Oh, okay. Because you have this.
If the Earth is if the Earth is 8,000 miles across, and the International Space Station is orbiting the Earth at 250 miles altitude, where are they? Are they out here? If the Earth is 8,000 miles across and the International Space Station is 250 miles above the surface of the Earth, tell me where to go.
I mean, closer, actually more
closer.
to
It's like right about there.
Yeah.
Right about there. The International Space Station is just skimming the Earth's surface above the atmosphere. Above the atmosphere. And to put this in a climate science context, the Earth's atmosphere compared to Earth is thinner than the skin of an apple compared to an apple. Let that sink in. Okay, so they're skimming just above the surface of the Earth. Have they gone far from the Earth?
No.
No. So the force of gravity exerted by Earth on the astronauts is almost the same as what it is when they're standing on their bathroom scales in their bathrooms on the surface of the Earth. The astronauts cannot be weightless, right? It's like if if I weigh almost the same as what I weigh on the surface of the Earth at the same altitude above the Earth as the astronauts can't be weightless because the force of gravity exerted by Earth on them, their weight is almost the same as what they weigh on the surface of the Earth. The astronauts weigh 90% of what they weigh on the surface of the Earth, as does the International Space Station, if you could find a bathroom scale big enough to put something bigger than a football field on. So what's the problem? What's the problem here?
Gravity is still exerting a force, right?
Yes, and
You're floating around.
and they're floating around where there's no gravity. And the vast majority of people walking the face of this Earth think that the astronauts are weightless because they're in space and there's no gravity in space. But that can't be true. We've got an inconsistency here. So I know you're in Arizona, the great state of Arizona, but I was born in New York. I'm a Bronx kid. And my favorite building is the Empire State Building. So now you gotta really follow me on this. So I'm going to go to the observation deck on the 104th floor of the Empire State Building. I'm going to go up in an elevator all the way to the 104th floor. And by the way, important note, the elevator has no windows. Ooh, it's one of those classic elevators. So what I do is in my elevator, I bring my bathroom scale because I told you I have this problem. And just before I went to the Empire State Building, I stopped at a kindergarten classroom and I pulled out one of those little chairs. And what's interesting is if I stand on that chair, I will be a foot above the floor. So I put the chair in the elevator with me. I have my bathroom scale in front of the chair. And I then go to the 104th floor of the Empire State Building. The doors open up. And it's sort of like the elevator car is part of the 104th floor. I can see people walking around up there. They can walk in the elevator. They can walk out of the elevator. Okay, so I do my experiment. Now, first of all, is the Empire State Building far above the surface of the Earth?
Not relatively
Nope.
to
No, certainly
yeah.
not compared to Mount Everest or a mountain 47 times higher than Mount Everest. Okay, that's important. So I get in my elevator, the doors are open, and I step on my little kiddie chair, and I'm a foot above the floor of the elevator, and I step down on my bathroom scale. Not a trick question. What do I weigh?
The same.
The same.
The same as what I am on the surface of the Earth, because the Empire State Building is on the surface of the Earth. It's a tiny little structure. Okay, but as a scientist, I believe in reproducibility. I'm going to do my experiment over again. So I get back up on my little chair and I'm about to walk onto the bathroom scale. But what happens is, as I'm about to walk off the bathroom scale, the doors close and somebody does a really bad thing and cuts the cable holding the elevator. What happens?
It stops.
It starts to drop. And what can you tell me about the speed of the elevator and everything inside it, like me, the bathroom scale, and the chair?
It's
And
going real fast.
It'll be accelerating every second.
It's accelerating, so the speed is increasing. And what's causing the speed to increase? Why is it accelerating?
gravity.
Gravity.
The force of gravity from Earth exerted on me, the bathroom scale, and the elevator car are causing it to accelerate under the action of gravity. It's called the acceleration due to gravity. Another way to say it is me, the bathroom scale, the chair, and the elevator car are falling under our own weight. Everybody with me on that?
Yeah.
Okay, so now, will the elevator car keep accelerating?
Until it hits maximum.
Well, I know we don't want to think about what could happen.
Till it smashes and you're all dead.
But yes, but before that happens, does it keep accelerating?
I don't know.
Yes, I think it's keep the same acceleration rate of.
So what fills the elevator shaft?
Air.
What does the air do?
well, I mean,
It's gonna
trying to
be
be resistance. Well,
There is lift.
Friction, air friction.
It's going to
gonna
cause
be
a drag
moving
force,
gravity.
right? It's going to cause a
Okay,
drag force. So
that's-
as an
okay.
example, if I like to parachute and I jump out of a plane,
Mm.
for the first few seconds, I am accelerating, but it turns out that the drag force due to the air resistance increases as my speed increases to speed squared. So what's happening is the drag force is going to slow me down and slow me down. Well, it'll slow the acceleration down until finally I reach what's called a terminal
Velocity.
velocity,
Oh,
and
it's
I
been a
can't
long
go any
time.
faster. And it turns out for a human being, the terminal velocity is about 100 miles an hour. But you're not going to survive landing at 100 miles an hour, so you probably want to deploy a parachute, which will dramatically increase drag so that you can go and parachute another day. Does everybody understand how air works? So what I'm going to do is I'm going to suck all the air out of the elevator shaft. And the car that's going down in the elevator shaft, I'm going to make sure there's no friction between the car and the shaft itself, so there's no friction. So if that's the case, when the cable is cut, what is the only force acting on the elevator?
Gravity.
Gravity. And that kind of falling has a special name.
Free falling?
Free fall.
Oh,
It is free of any other force. It is free of any other force. So now the elevator, me, the bathroom scale, and the chair are going to be accelerating down at the acceleration due to gravity. There's no other force acting in there. Does anybody know what the acceleration due to gravity is?
Is it
There's a number.
9.8 Newton
Meters per second.
Okay, so is it Rini? Rini said the acceleration due to gravity is 9.8 meters per second per second. Can anybody tell me what that means? Rini, do you want to tell me what 9.8 meters per second means? We don't think about that, right?
really?
We
So-
kind of memorize that number.
It's the change in velocity per unit time.
Yes, so that means that every second the speed increases by 9.8 meters per second. In the English system, every second the speed increases by 32 feet per second. And you know what? That's a number that you can memorize, and absolutely no learning has taken place. None. If you're going to teach something, you need to have a guttural emotional reaction from your students so conceptually they get it. If you're just asking them to memorize stuff, that's meaningless. I don't know what that means. So the way to do that most effectively is to build a bridge to the familiar, recognizing that they know their world. They navigate through it every day, hopefully successfully. So let me put it in a context that you will understand. The acceleration due to gravity means that every second your speed increases 20 miles an hour. Every second your speed increases 20 miles an hour. After 10 seconds, you're moving 200 miles an hour. After 100 seconds, you're moving 2,000 miles an hour. The acceleration due to gravity is big. Does everybody get that? Did you get that emotional response? Okay. So
Say that one more time.
yes, the acceleration due to gravity means that your speed is increasing 20 miles an hour every second.
Okay.
So after the first second, you're moving 20 miles an hour. After 10 seconds, you're moving 200 miles an hour. After 100 seconds, you're moving 2,000 miles an hour. And so what is accelerating that we're talking about here? What name the objects that are accelerating?
The scale, the elevator, you, and the chair.
Yes. Okay, cool. So now, what happens the moment I step off the chair the second time I do the experiment when the cable is cut and there's no air in the shaft and there's no friction? Tell me what happens to me when I'm standing on the chair and the moment I'm stepping off the chair thinking I'm going to the bathroom scale, the cable is cut. What happens?
You can go up a little bit.
This time you will
Maybe
notice
hit
and
your
you have
head.
low weight.
Well, let me say that all of us are accelerating down at the same rate. Okay? So if the elevator car goes down 20 feet, will the chair go down 20 feet in the same amount of time?
Yes.
I don't know.
We are all accelerating
At the
at
same
the
rate.
same rate. It doesn't matter if
Okay,
you're
well, then
dropping
yes.
a bowling ball or a bulldozer, or a feather. If you're dropping it from the same altitude with no air, at the same time, they will hit the ground at the same time. The acceleration due to gravity has nothing to do with the mass you're dropping. And go look for a YouTube video, because an astronaut did this experiment on the moon. He dropped a hammer and a feather from the same height at the same time, and it hit the ground. The both of them hit the ground at the same time. And if you have a problem conceptually with that, here's the deal, okay? I'm a big guy. I'm holding a Volkswagen Beetle in one hand. Okay, everybody with me on that?
Mm.
Okay. Is it possible that Volkswagen Beetle has a mass of an equivalent of 150 bowling balls?
Yeah.
I think it would be more than
Right.
that.
I mean,
You take
mass.
or whatever number of bowling balls you
Okay.
want, okay?
Okay.
Let's say it's 200 bowling balls. If I have 200 bowling balls that are identical, it's the same mass as my Volkswagen Beetle. Got it?
Okay.
So
Okay.
I'm dropping my Volkswagen Beetle and one of those bowling balls from the same height at the same time. And the question is, are they going to hit the ground at the same time? Right?
Yes. Yeah.
But that Volkswagen Beetle is the same as 200 bowling balls that are identical. So if I drop one bowling ball and 200 identical bowling balls from the same height at the same time, will all the 201 identical bowling balls hit the ground at the same time?
I think
Yes.
so. Yes.
So it doesn't matter what the mass of the object is. So now, if I'm in this elevator and we're all accelerating down at the same acceleration, we're increasing our speed 20 miles an hour every second. If the elevator car goes down 20 feet in a certain period of time, will the chair also go down 20 feet in the same amount of time? Will Jeff go down the same 20 feet in the same amount of time? And what about the bathroom scale? We're all going
Yes.
down together. So here's the point. When I stepped off that chair, how far above the floor was I?
I think you said a foot.
1 foot. And as soon as I was stepping off the chair, somebody cut the cable and we started accelerating down. So now, if I am stepping down in the direction of the elevator's floor, isn't the elevator's floor also moving down at the same acceleration?
Yes.
So if I move down 20 feet, will the elevator's floor also move down 20 feet?
Yes.
Yes.
Can I catch the floor?
No.
No, not until it hits.
Let's say you like the hitting part.
I'm sorry. You just keep picturing me crashing.
Okay. All right. So let me say it again. As soon as the cable is cut, we're all accelerating down at the same acceleration, the acceleration due to gravity, which means that I was thinking I was going to step down to the bathroom scale. But if the elevator floor, if I move down 20 feet in a certain period of time, the elevator's floor is going to move down 20 feet in the same amount of time. And you just told me I can't catch the floor. So what do I see in that laboratory?
You
Weightlessness.
don't have weight?
I'm floating a foot above the floor. And I look around and I say, who turned gravity off? There's no gravity in here. Now, do I get to see that the different floors of the Empire State Building are flying by me at an ever increasing speed? Why not?
There are no
Yes, yes,
windows.
There's no windows.
Oh.
Right? It's like I stepped onto the bathroom scale and I weighed the same as what I weigh on the surface of the earth, and I did the experiment over again, and now for some reason there's no gravity whatsoever. Somebody turned off the gravity switch. I still hear Barry Manilow playing on the elevator.
So you don't know you're going to die.
Bluetoothed in. And so here's the irony, okay? The irony is that whenever you are in a freely falling laboratory, and it's freely falling because the force of gravity exerted on it is causing it to plummet at an ever-increasing speed. The irony is, in a freely falling laboratory, everything will behave as gravity is turned completely off. That's what weightlessness is. Microgravity is the technical term for weightlessness. An experiment in microgravity is an experiment in a weightless environment. Is everybody with me on what I just said? Okay, so now you don't realize this. I'm a very special kind of human being. In fact, I'm from another world because there's no air in this room. And so you're not hearing my sound. I'm just thinking stuff and you're hearing me. There's no air in this room. Is this the elevator? There's no air in this room. Is this the elevator?
It can be.
Yes.
So
Yes.
what you're saying is this is in free fall.
Yes.
There's no air in the room. The only force acting on it is gravity. It's falling under its own weight. Can somebody explain to me the trajectory of this ball if I throw it with a little force? And then, so I give it a push, I push it, then it leaves my fingers. It's no longer in contact with my fingers. What is the trajectory of this little ball going out?
It'll go and
It
eventually
arcs,
go
right?
down.
And then it
Yeah.
hits the ground. What if I throw it a little faster? What happens to the new trajectory?
Go a little further.
A little farther and hits the ground. Okay. If I throw it, once it leaves my fingers, what is the only force acting on it? What's the only push or pull acting on it?
Gravity.
Gravity. So once it leaves my fingers, is it in free fall?
No.
No.
Well, it
not
does
if
have a
you-
little bit of the potential, like kinetic energy that you
Right.
apply.
So,
Right.
so what I've done is I've given it a little speed when it leaves my fingers, but once it leaves my fingers, the only force acting on it, a force is a push or a pull, right? My fingers pushed it. I gave it a force. I imparted a force to it. That's brought it from 0 to a certain speed. But once it leaves my fingers, what's the only force acting on it?
Gravity.
Which means it's in free fall.
Mhm.
Now, if I keep throwing it faster and faster, once it leaves my fingers, what happens to the trajectory?
I mean, it
It
will
just
be
goes
Gets
further.
bigger and bigger and bigger until finally, if I throw it really, really fast, the trajectory will be so large it will swallow the entire Earth, and it'll come back in my hand in 90 minutes.
Okay.
Right? Did everybody
Yes.
see what I just did? And
Yeah.
so,
It'll rotate around there.
ladies and gentlemen of all ages, boys and girls of all ages, this is the elevator, and this is the International Space Station.
Okay.
The International Space Station is in free fall. It is the elevator, but it is in continuous free fall. And as G said before, the force of gravity exerted by Earth on the International Space Station, its weight, is causing it to go around the Earth instead of just flying off into deep space in a straight line. The International Space Station is in free fall around the Earth.
Nice.
And that's why the astronauts appear to be weightless. Is everybody with me on this?
Yes.
Yep.
Great
So now,
explanation.
all of this is on the website. It's all written on the website because I wrote it. And so the idea here is to say, you want to understand the role. So here's the storyline. So follow me. I'm gonna do this really fast. So you want to understand the role of gravity in something. So I said, what needs to be the independent variable? You said gravity. You said we need to change gravity. I said, but we can't, because it's the force of gravity exerted by the Earth on everything. And so then I said, what do you think happens to gravity when you go farther from the Earth? You said it gets less. It lessens, right? It diminishes. I said, oh, well, maybe we can go to a really far, if we go to the International Space Station, maybe gravity is so weak there, we can do the experiment, that way. So I asked you what the highest mountain on Earth was. You said Mount Everest. I said, not tall enough. We need one 47 times higher because that's a way cool mountain. on the top of that mountain, I'm at the same altitude as the International Space Station, 250 miles above the surface of the Earth. And they're floating around in the space station, but I look down on my bathroom scale, I weigh 90% of what I weigh on the surface of the Earth. So then I said to you, okay, the Earth is 8,000 miles across, the International Space Station and the top of my mountain is 250 miles above the surface of the Earth. Where is it? You said down here. You said down here. I said, that's right. Have you gone far from the Earth? You said no. And then I probed a little deeper, and yeah, that's why they still weigh 90% of what they weigh on the surface of the Earth, because they haven't gone very far from the Earth, which is now a really big predicament, because if I weigh almost the same as what I weigh on the surface of the Earth, the astronauts do too. And I said, what's the problem? And I'm not sure if it's not Rini, it's not Debbie. Debbie's friend said, well, they're floating around. Where's gravity? And I said, yeah, what's the deal with that? So I took you to the top of the Empire State Building. You told me the Empire State Building is not very high because it's a tiny little structure compared to like this mountain I'm talking about. And so I put you on this little chair and I had you step down and I said, how much do you weigh? And you said, I weigh the same as what I weigh on the Earth. I said, yeah, that's great. It was not a trick question. So then I did this experiment over again. I cut the cable and we talked about the acceleration due to gravity. You said that the speed was going to increase. You said the speed was 9.8 meters per second. I redefined it in something you can say, oh, wow, okay? And so then I said, well, is it going to keep accelerating? And then Debbie's friend said, well, eventually we're going to splat on the bottom floor. And I said, well, let's not go there. And then we talked about the air inside the chamber. You told me air was inside the elevator shaft. And so then I gave you the example how air is causing resistance. So we took all the air out of the elevator shaft. We made sure there's no friction between the car and the sidewalls. And then I said, what's the only force acting on the elevator? And you said gravity. And I said, what's going to happen? And you said it'll keep accelerating. And then I told you, yeah, it's a really big acceleration. And then I said, well, are we all accelerating at the same acceleration due to gravity? Yeah, and there wasn't quite a consensus there. Most people were quiet, but Debbie's friend said, I don't know if we're accelerating at the same rate. So I went to the feather and the hammer thing that the astronaut dropped on the surface of the moon. Go to that video. And then I said, okay, here's a Volkswagen Beetle, 200 bowling balls. They weigh exactly the same. They're the same masses. If I drop the Volkswagen Beetle and the bowling ball from the same height, will they hit the ground at the same time? Well, I'm not sure they will. But wait, the Volkswagen Beetle is 200 bowling balls. So let's drop 201 bowling balls. Are they all going to hit the ground at the same time if they're starting from the same altitude? You said yes, which means that the acceleration due to gravity has nothing to do with the mass you're dropping. So I said, what's happening to me, the chair, the bathroom scale, and the car? You said they're all accelerating down at the same rate. Great. I said, okay, if I go down 20 feet towards the floor, is it true that the floor moves down away from me 20 feet? You said yes. I said, can you actually catch the floor? You said no. I said, what do you see? Do I see the stories zipping by in the elevator? Debbie's friend said, no, because there's no windows in the elevator. And so I said, what do you see? And you said, you're floating in the middle of the elevator, a foot above the floor. Who told this story? Anybody? You want to? Did I tell that story, or did I just tell you tell
You
this
did.
story? Right? Do you feel a sense of ownership in this story?
No.
As opposed to
Part of
me
the
just
story.
writing stuff on an overhead and having students memorize it? You brought your knowledge to bear. We did this together. We took the journey together. And then I showed you that the irony in a freely falling laboratory is everything will behave as if gravity's turned completely off, even though it's the force of gravity causing it to plummet at an ever increasing speed. And then we used ping pong balls to show you that the International Space Station is in continuous free fall.
I'll explain
Everybody with
it.
me on this?
I had to eat lunch.
Does it all make sense? Can you, if you have a pot of coffee and you go, well, at least 2 cups of coffee, and you go to the page where that's all written up, do you think you can get this across to your students?
Yeah, I'll make you lots of coffee.
Okay, so we were talking about you. Were your ears burning?
I was eating my lunch and I didn't want to be rude chewing on
No,
screen.
that's good.
Yes.
That's good.
And I'm
That's
Debbie,
good.
by the way. This is Maria.
Oh, you're Debbie. Okay, Debbie.
I'm
All right,
Debbie.
good.
That's Maria. Yeah.
Okay, so
But I heard everything.
that's good. That's good. So here's the deal, everybody.
That you
Okay,
were
here's the
gonna
deal. Here's where I'm going to pull it all together. All right. A microgravity experiment is an experiment in a weightless environment. What is the motivation for doing it? I want to understand the role of gravity in something. I can't change the gravity variable, so I trick the experiment. I take the experiment to the International Space Station where it will behave as if gravity's turned completely off. And what other experiment do I need to do at the same time?
Your control, which is ground.
Yes, I have to do the same experiment on the ground in gravity. That's my control. So when I bring the flight experiment down and I put them side by side, this one operated in the seeming absence of gravity. This one operated in gravity. And I compare the behavior of what I'm studying to look for discernible differences in behavior, which will be the telltale sign of the role of gravity in what I'm studying. Does everybody understand how simple a microgravity experiment is?
Yeah.
It's classic experiment design with a twist. You want to change the gravity variable, you can't. So you drop it. And it will behave as if as gravity's turned completely off and you compare it to a control experiment on the ground. Everybody with me on that? Pam likes this, I can tell. Okay. So now, anybody have any questions about chapter 4, which is the hardest chapter? What is a microgravity experiment? Oh, cool. Okay, so now I'm going to remember to stop the recording.